Hello everyone, I'm Wei Zhang from the University of Tokyo. I'm here to give the presentation about our paper, EnergyHair Sketch-Based Interactive Guide Hair Design Using Physics-Inspired Energy. The capture of real human actors as virtual actors has become popular in the entertainment industry owing to the advancement of multi-view stereo techniques such as the light stage. With these techniques, virtual actors, for instance, digital ME, are almost indistinguishable from the real actors. However, capturing hair is difficult. That is because sometimes a strand of hair is thinner than a pixel. It would be challenging to capture hair automatically. Also, hair has high specularity, which means hair's color may differ rapidly between neighbor views. Another reason is tight occlusion for hair in images. It is difficult to estimate the shape of entire 3D hair strands based on outside appearance. Therefore, conventional multi-view stereo cannot be directly used for hair. Actually, hair design for virtual avatars is still a manual task. However, it is not so easy to manually design physically reasonable hair. This video shows our design using Maya Exgen. We can see that during the design, hair is floating in the air. And hair is going under the skin too. Also, the view needs to be changed frequently to design plausible hair strands. And there are a lot of works that have tried to improve these circumstances. Among them, some work focused on detailed hair capture. This work generates highly detailed hair geometry, but it is still difficult for artists to design. The hair simulation has models such as the mass spring model and superhelices model. However, it is not intended for use in interactive modeling. Some sketch-based hair designs consider interaction, but it is still difficult to edit the 3D shape of guide hairs. Therefore, we want to input users to the sketches and generating 3D hair strands. However, directly using the 2D sketch information for 3D reconstruction cannot work because of lacking the depth. To solve this problem, we introduce physics-inspired energy so that it is possible to reconstruct 3D hair strands from 2D sketches. Here is the overview of our work, EnergyHair. Our workflow includes two parts, the offline pre-computation and online design session. The offline pre-computation uses real human images to reconstruct a 3D human head as well as multiple viewpoints, which would support users' 2D sketches. Also, we pre-compute necessary data to suggest sketch for users. The online design session uses the energy minimization method to balance the 2D user sketch and 3D hair strand. We support three operations for users to interactive design guide hair. When users left-click to draw a stroke for one single strand of hair, the sketch suggestion system will show a red line to suggest the shape of the current designed hair strand. By right-clicking, users can drag the strand anywhere they like. During dragging, the editing hair strand may appear in different colors representing physical validity. From pink to blue, hair becomes more and more physically plausible. While to make hair look physically reasonable, users can press the middle scroll button to use sketch relaxation, which would decrease the physical unreal part of the current hair strand. But how do we achieve these tools? Well, let me introduce our method. The key is to optimize an energy function, W plus K. W is the energy potential energy. V devote 3D hair strand, and theta devote physics parameters. Elastic potential energy describes the physical plausibility of the 3D hair. And the key is sketching energy. It penalizes the difference between the input 2D sketch and 3D hair strand. First, let me go deeper into the sketching energy K. K prime is the sketching energy of a single hair. Under each viewpoint, each hair has 2D elastic potential energy and distance energy between sketch U and hair strand V. For distance energy, instead of naive way to compute the distance from points on hair strand to sketch line, we use spline representation to replace the polyline. Ours will be the distance from the points on the hair strand to the spline curve of the sketch. Finally, we sum all viewpoints energy to obtain the K prime. Then the other energy of our method is elastic potential energy. W prime is named for a single hair's energy. It also contains two parts. 3D elastic potential energy computes hair strands stretching and bending energy, which means this kind of energy is only with a straight rest configuration. Then we also add the gravity and penetration depth from the head to our elastic potential energy. We also have an automatic sketch suggestion system. This system requires images of a real human head. Then we compute the orientation field by applying the Canny filter. Because we do not need such a high-resolution orientation field, we blur and downsample it. The orientation fields represent the hair strand's directions from 0 to pi. Also, we introduce the similarity field to identify the hair region roughly. This field shows the average difference between one pixel's orientation and its neighbors. The darker pixel is, the more similar with the round neighbors. Here, I will show the procedure of the sketch suggestion system. For the current suggestion mount point, the suggestion sketch will grow under the direction of an acute angle and keep on growing until it meets a point that has a similarity beyond the threshold. Then we will get the final suggested sketch from the mount to the end of the hair strand according to the input image. Okay, that is all for our method. To show the efficiency of our spline representation for distance energy, we compare the results of our spline distance with the naive distance. Through the videos, we could see that ours can successfully achieve the global minimum. This is the video sample of our EnergyHair made by an artist. More results shown here. For the limitation, our physics model is simple, only with straight rest configuration. Users can make straight hair easily, but curly hair is difficult to design. In the future, we plan to include additional physics-related parameters such as preparedness in online optimization and develop a real-time preview for hair results, not only guide hairs. Thanks for your attention. Please feel free to give your questions.